Hey guys, here is your next set of notes for Unit 5. This is on atomic structure and light, part 3, so kind of continuing on what we've been talking about in class. Your question of the day is, how is it possible for hydrogen with only one electron to give off 4 different colors of visible light? So you may need to pause the video and go ahead and answer that on your notes. Okay, so this is possible because that single electron is getting excited and going to higher energy levels. As it falls back down to energy level number 2, it's releasing visible light. So there's 4 different locations that the electron's going to fall from. That's why we can see 4 different colors. All right. So here's a question. What is the universe made of? Everything in the universe falls into 2 categories, matter and light. Matter, as we have seen, is made of atoms, and atoms are made of protons, neutrons, and electrons. Light is also energy, but more specifically, it's electromagnetic radiation. If you can touch it, it's matter. Otherwise, it's energy or light. There are 3 things we can measure about a light wave. We can measure its speed, its frequency, and we can measure wavelength. So just like last class, frequency is going to be this letter that looks like a V. It's a number of waves that pass through a particular point in 1 second. The unit is waves per second, which is also known as hertz, Hz. Wavelength is this lambda symbol. It's a distance between 2 consecutive waves. The units are usually meters or nanometers most of the time. And then we can measure speed, which is letter C. The number of meters a light wave can travel in 1 second. The unit is meters per second. So here's all of this stuff labeled on a wave. From one point in the middle to the top of the wave is called amplitude. From one wave to another is your wavelength. This bottom part is called the trough, and that top part is called a crest. So I have a high frequency wave here and a low frequency wave on the bottom. They move at the same speed, the speed of light, because these are light waves. The speed of light, or C, is equal to 3 times 10 to the 8th meters per second, which is 300 million meters in 1 second. So very, very, very fast. That means a light wave can travel around the Earth 10 times in 1 second.
Next week, Chevis, please come to the office. Next week, Chevis, come please to the office.
Sorry about that. So my equation for speed of light, which we used last class, is C equals wavelength times frequency. Yeah. Okay, so let's do an example. A microwave oven that cooks a hot dog emits a light wave with a wavelength of 2 times 10 to the negative 2 meters per wave. What is the frequency of this light wave? So we can go ahead and use this equation. I'm actually going to do this with you on my notes. Okay. Okay, so I know that speed of light equals wavelength times frequency. And then I can just plug in my numbers, okay? Since I'm trying to solve for frequency, I can just do speed of light divided by wavelength, which is 3 times 10 to the 8th divided by the wavelength that they gave you, which was 2 times 10 to the negative 2. That will give you your answer for frequency. So I went ahead and solved that for you, and I got 1.5 times 10 to the 10 waves per second, which again is called hertz. Okay, we'll come back to that in just a minute. Electromagnetic radiation, or energy, or light, or whatever you want to call it, includes visible light, infrared, UV, gamma rays, X-rays, TV waves, radio waves, and a lot of other forms of light. Our eyes are only equipped to see the visible light. All other types of light or energy are invisible to us. But our bodies are sensitive to other types of light or energy. For example, pit vipers can see infrared color, which is basically just heat, something that we cannot see. Visible white light is a mixture of all the colors of the rainbow. Speed of light in a vacuum is going to be constant for all of these. It's the 3 times 10 to the 8th. So here's an example of an electromagnetic spectrum. I believe you have a few questions on your notes about this, so you might need to pause it and look at this picture a little bit better. But on the left side, I have gamma rays, and it goes all the way to the right side where there are radio waves. So my left side is very small waves, and then on the right side, it's very, very large waves. Here's another picture for you. As I go towards gamma rays, that's going to be a higher frequency. So the higher your frequency is, the more energy that wave has. On the right side towards radio waves, it's really low frequencies, which means my energy is smaller, but my wavelength is longer. Here's one more picture for you. One thing I wanted to note on here, AM radio waves, the length is 3 football fields long, so very, very, very large waves. And if you look at the top of this picture, it kind of shows you what that wavelength looks like and the frequency looks like. Over near gamma rays, that frequency is so incredibly high. Here's one more picture. I just like this one because it gives you the size of the wavelength on those pictures at the bottom, and it shows you kind of an example of something that would be the same size, which is very interesting. So the visible spectrum is between the size of a virus and the size of a protozoa. Colors of visible light waves depend on their wavelength or frequency. The different kinds of visible light can be arranged by wavelength into an electromagnetic spectrum. Different colors of visible light have different energies, where violet light has more energy than red light. So purples have more energy than red. Visible light ranges from about 400 to 800 nanometers. That's the wavelength. Black light, which is really close to UV light, causes certain objects to be fluorescent or to glow. Fluorescent UV lights are absorbed by electrons and atoms and then emitted as longer visible wavelengths, such as violet or purple visible light. So if you ever look at a black light, it kind of looks purple. This is why. Here's a good picture of what visible light is looking like. So at the top, I have my reds. Those are really long wavelengths, so lower energies. And as I get towards purple, it's closer to 400 nanometers. It's a shorter wavelength, which means higher frequency, higher energy. So how do matter and energy relate? We know that matter and energy have the ability to interact with each other. Matter can absorb or give off energy. Until recently, most people thought matter absorbed and released energy continuously without stopping. So when solids are heated, they emit light of all different energies. A warm solid at 7,500 degrees Celsius will glow red, and a hot solid at 10,000 degrees Celsius will go blue, which makes sense. The hotter it is, it's usually blue. At extreme high temps, there were some energies not being emitted at all. Certain energies in between weren't emitted as well, which didn't make sense. So, have you ever seen a pot being heated? It gradually heats up and it gradually cools down, which means the energy change is continuous. It emits all energies all along the way. Until Max Planck came along and studied this very intensely. He was told by his professor not to study physics because all the famous discoveries have already been made. So he actually went on to win the Nobel Prize in 1918. He assumed vibrating atoms in a heated object gave rise to emitted energy. Atoms and molecules could absorb energy only in definite amounts called quanta, not continuously. He said that energy was not absorbed or given off continuously, but in definite amounts or jumps of energy. This is why only certain types of energies were seen. He called this quantum theory. So Planck's constant, like we talked about last time, this comes from him. This is where quantum theory comes from. This would be the same as driving in a car, but only being able to drive at 10 miles per hour, and then 20, and then 30, but never in between each one of those. Does a pot on your stove heat up or cool down like this? No, it usually gradually cools, heats and cools. So how can this be true? Other scientists thought Max Planck was crazy. No one believed what he was saying. They just thought it was all nuts. He almost lost his entire reputation to this quantum theory. It is obvious that things absorb and release energy continuously. Think of fires, pots, pans, human bodies, water. Experimentally, the quantum assumption part of his theory was a little bit shaky. Even Planck tried to eliminate it from his own theory. So a scientist came along and helped him out and kind of saved the day by helping prove him right. This guy was Einstein. He would win his first Nobel Prize for an experiment called Photoelectric Effect. So here's kind of a picture of what this looks like. On the left side, I have this red light being shot through sodium. There's no electrons emitted at all. So they started changing the color of the light, which changed the wavelength and the frequency. The red light, no electrons were emitted. The blue light, no electrons were emitted. And now with violet light, which is, remember, a really low wavelength, a high frequency, and a high energy, lots of electrons are emitted. If energy absorption was continuous, what should have happened when the amounts of red energy increased? It should have more and more electrons that were leaving, but nothing happened when the red light amount was increased. This told Einstein that energy absorption was not gradual or continuous, but occurred in definite amounts called quanta, which is what Planck was saying earlier. The real question was, how did a light wave move matter? An electron is matter, right? Have you ever had a light wave move you? And here's kind of a picture of what's happening. Many scientists laughed at Einstein. They said his idea was ridiculous, or it's impossible for light to move an electron or any matter. So he said, light is made of matter. Each light wave contains tiny little particles called photons, not protons, but photons. Increasing the amount of waves is simply increasing the number of photons, but it's not increasing the energy of each wave. However, if the energy of these photons is related to their frequency, this would explain higher frequency light waves can knock the electrons out of atoms, but low frequency light waves can't. High frequency light waves have more photons that have more energy to move matter. So everything's related back to energy. Here is an example of that in this picture. In this longer wavelength, there's not as many waves per second. That's what frequency is, waves per second. So the longer the wavelength, the less waves per second you have. The bottom one, it's many waves in 1 second, so the frequency is a lot higher. So the top has not very many photons carrying energy, the bottom has lots of photons. Okay, so in this photoelectric effect, it says the only way to move matter is with matter. Why then do light waves not move your electrons or atoms? They do. Remember, every matter in the universe is sensitive to photons of a particular light. So if we're talking about waves, what light waves can damage your atom? Think about all the different types of waves. UV waves, X-rays, gamma waves can remove electrons from your DNA and cause permanent damage to your cells. So they are doing something. And visible waves do not have enough photons to cause any damage. In this atomic picture, the energy of the photon must overcome the binding energy of the electron to move to energy of the electron to the nucleus. So I'm going to show you a picture in just a second. If the energy of the photon exceeds the binding energy, then the electron is given off. Here's an example of that. So I have this wave coming in. and colliding, my photon collides with the electron. If there's enough energy from the photon, then that electron gets taken out of the atom. The result of Planck's and Einstein's work led to this equation: energy equals Planck's constant, which is h, times frequency. And we talked about this equation a little bit last class. So again, E is the energy of the wave, h is Planck's constant, or 6.624 or 26 times 10 to the negative 34. And the little v is frequency, which is measured in hertz. It makes sense since the energy of a light wave will depend on how many photons are passing through a material, which is dependent on frequency. Let's do another example. The frequency of a red laser in a DVD player is 4.29 times 10 to the 14th waves per second. What is the energy of this light wave? So I'm going to pull up my notes. So I'm going to use that equation that we just learned about, energy equals Planck's constant times frequency. I'm looking for energy, and I know Planck's constant, 6.626 times 10 to the negative 34, and I know frequency. It gives me frequency. So I'm going to multiply these two things together to get energy. So I went ahead and did that, and I got 2.84 times 10 to the negative 19 joules. Energy is always measured in joules. This seems small. This is only the energy of one photon or light wave. Okay. How does all this change what we know about an atom? In 1924, Louis de Broglie, probably said that wrong, proposed that because light waves act somewhat like matter, then matter must act like light waves. This means that all matter, ducks, bowling balls, planes, electrons, even us, has to travel in waves. This didn't make sense since most people could see that objects traveled in straight lines. In 1927, two scientists at Bell Laboratories proved that de Broglie was right. They took X-ray crystallography pictures of atoms, and they saw that electrons actually traveled in waves. So this is what we know today, and you probably have not talked about this yet in chemistry, so this is kind of new to you, but electrons don't just follow these circular paths, they're traveling in waves. This caused the model of the atom to be redesigned again. So here's what atoms probably look more like. Not the Bohr model, not the nuclear model, this model where electrons are going in a wave. So here on the left, I have a hydrogen atom with its one electron circling the nucleus. And then on the right side, I have another atom with all the different waves. If all matter travels in waves, then why can we not see the wave motion of normal objects? If you were to measure the wavelength of a duck or plane or bee, you would see relative to the size of the object that its wavelength is actually really, really small. Electrons are already so small. This means that the wavelength of an electron is actually large compared to its size. So our wavelengths are really small, but an electron's wavelength compared to its relative size, which is really tiny, means that its wavelength is big. Its wave-like motion is going to affect the atom and the structure. Our waves are what we're giving off is so small, or so small that we can't see it. So de Broglie derived an equation. This equation allows us to calculate the wavelength of anything, so us, a bus, a basketball, whatever, of anything with considerable mass, meaning not light. So it's wavelength times Planck's constant divided by mass times velocity. The mass needs to be in kilograms since these are large objects. Velocity has to be in meters per second. So I have another example for you, if I can get it to pull up. What would be the wavelength of a bus traveling 28.82 meters per second with a mass of 4,535 kilograms? So this is already plugged in for you on my slide. I'm just going to use that equation and plug in all my numbers. So I have Planck's constant on the top. On the bottom, I have the mass that's given, and then I have the velocity that's given. This is always given to you in the question. So I'm multiplying on those bottom two numbers, and then doing Planck's constant divided by the bottom number. I got wavelength as 5 times 10 to the negative 39 meters. So this is a bus, something that's huge, but the wavelength is so small that we can't actually see it. It's too small to observe. But for an incredibly small particle like an electron, this kind of wavelength would be very noticeable. All right, so that is it for today. Please let me know if you have questions and go ahead.